Okay, so good evening. I think we'll start today's session. So this is the week third of the live interaction session of the NPTEL course, Introduction to Atmospheric and Space Sciences. So today we will start by solving a couple of problems. So if you guys remember last class, we were discussing about the vertical structure of atmosphere. What are the different layers in the atmosphere? How the temperature is changing as we go up in the atmosphere, how the pressure is changing, how the density is changing. So very interesting facts and different aspects we covered in the last week. So today we will begin with solving one or two problems related to what we learned in the last class. Okay. First question. Suppose in an isothermal atmosphere, just a second, someone wants to join the call. Yeah. Suppose in an isothermal atmosphere, which is basically dry, with surface temperature T0 is equal to 288 Kelvin, what will be the pressure at an altitude of 4 kilometer from the Earth's surface? Assume surface pressure is 1000 hectopascal. Okay, so the question is, suppose there is an isothermal atmosphere which is basically dry. Dry in the sense there is no water vapor content in the atmosphere. And they have given the surface temperature to be 288 Kelvin. And we basically have to find the pressure at an altitude of 4 km from the Earth's surface. Assume surface pressure is 1000 hectopascal. So if you remember, we derived an equation to find the pressure at a height set if we know the surface pressure in an isothermal atmosphere. So we did two derivations. First one was for the simplest case of an isothermal atmosphere, and the second one was more a realistic case where the temperature was actually decreasing with respect to height. So this question basically they have already given that it is an isothermal atmosphere. So we have to use the equation P is equal to P0 e raised to minus Z by H. Can you tell me what are these terms? P is basically, what is P? Do you guys remember this equation? What is P? Okay, what is P0? You can type in the chat box also.
Pressure?
Yeah. Pressure at what level?
Pressure at ground.
Yeah, pressure at surface is P0 and P is the pressure at the height Z. So P is a pressure at height Z, which we basically have to find out. P0 is the surface pressure Z is the height, H is the scale height, which we learned in the last class, which is the height at which the surface pressure reduces to, where the pressure is basically 1 by E times the surface pressure, P0 by E. The height at which the pressure reduces to 1 by exponential times the surface pressure. And it is given by RT by G. So these are the different terms in the equation. What all values are given? P0 has been given as 1000 hectopascal. 1000 hectopascal is basically hectares, 1 pascal is 100. Um, 1 hectopascal is 100 pascal. So 1000 hectopascal is 1000 into 10 raised to 2 pascal. Z is the height at which we have to find out the pressure, which is given as 4 kilometer, which will be 4000 meter. And scale height H we have to calculate from RD T by G. Why did I give RD? Because D represents in a dry atmosphere, or in case of dry air, what is the value of R? R is a specific gas constant that we learned um, in the last class, which is different from the universal gas constant R, which is having a value of 8.314. And RD is basically specific gas constant, which has different values for the gas that we are considering. So we learned that in case of dry air, the value was 287, and in case of moisture, it was around 461. So RD is 287 into temperature 288, and the acceleration due to gravity we know is 9.8. This we need to find out. Then what? Yeah, I think with these, once we know all these terms, we can basically calculate P. So first we can calculate the value of H. What will be the value of H, or scale height? Can you calculate and tell me? 287 into 288 divided by 9.8. What it will be?
It is 8434.285.
Yeah. What is the unit? So RD is basically have a unit of joule. RD basically have a unit of joule, Kelvin inverse, kilogram inverse, and T is having a unit of Kelvin. So joule, Kelvin inverse, kilogram inverse into Kelvin by meter per second. Meter second raised to minus 2 is G. Just a second, let me check the unit of RD. Yeah, Joule Kelvin. Yeah, Joule Kelvin inverse, kilogram inverse. It should be in meter actually. I don't know. I think I'm missing something. The value should come in meter. The value that you told us how much? 8,434 meter. The unit will be in meter. Uh, I think I'm missing something over here. Are you able to? Okay, joule. What will be the unit of joule in SI units actually? Joule is the unit of energy, right? Which is um, yeah, yeah, it will be meter. So joule will be kilogram meter second raised to minus 2. So that and G will be gone, which is in the denominator. Then kilogram will be gone. Kelvin will be gone. Eventually we will be left with meter. So it will be 8,434 meter. So if you write joule in terms of SI units, you will eventually get the unit as meter. So the unit of scale height is meter. So it will come around 8,434 meter. So that is the unit of scale height. Yeah. So now once we got scale height, we can calculate the pressure at height Z, which is P, as P is equal to P0 e raised to minus Z by H. Now we know the value of Z. P0 is 1000 hectopascal, which is 1000 into 10 raised to 2 into exponential of Z is given in the question, which is 4000 meter or 4 kilometer, divided by H is 8,434. Can you calculate and tell me what it is? Did anyone got the answer? How much it is coming? I'm sorry, I think I lost the connection in between. I don't know how long I have been gone. Just a second, let me share my screen again. Yeah, so we were basically trying to solve in case of an isothermal atmosphere, what will be the pressure at a height of 4 kilometer. If the surface temperature is given as 288 Kelvin, surface pressure is given as 1000 hectopascal. Yeah. So what will be the pressure at a height 4 kilometers? So the equation is P is equal to P0 e raised to minus Z by H. We found where H is the scale height. We found the value of scale height H as 8,434 meter. The unit of scale height is meter. And then now we have to find the value of P, which is 1000 into 10 raised to 2 surface pressure into exponential of 4000, which is the value of Z by scale height, which is 8434. So can you tell me how much you are getting? What will be the value of pressure at a height of 4 kilometer? Be the value. Can you just calculate and tell me? Did anyone got an answer?
No, ma'am.
Okay, where you are stuck, can you tell me? What is the issue?
I was not able to get the exponential part.
Okay, you guys don't have a you have a calculator? Uh, so the exponential of 4000 divided by 8434 will be 1.6. The value of the exponential will be 1.6. Like 1000 into 10 raised to 2 into 1.6. It will reduce into. So it was basically P is equal to 1000 into 10 raised to 2. The 10 raised to 2 is coming because it is given in hectopascal. We have to convert it into pascal. So P0 into exponential of Z, which is 4000, divided by H, which is 8434. It will have a value. There is a negative sign over here. I think I missed it here. So it will be exponential of minus 4000 by 8434. It will be 0.6. The value of exponential will be 0.6. So it will become 1000 into 10 square into 0.6, which will finally give you 622 into 10 raised to 2 pascal, or 622 hectopascal. This will be the pressure at a height of 4 km in case of an isothermal atmosphere. Okay, I hope it is clear. Now let's see another question. I hope this question is clear. Is there any doubt? rather than the calculation part. I think the equation and concept is clear. Yeah. So now, so we know that we don't have an isothermal atmosphere, right? The atmosphere, when we look at the temperature profile in the atmosphere, we have seen that the temperature is actually decreasing with respect to height, especially in the troposphere. For the first few 10 to 10, 12 kilometer, the temperature is actually decreasing with respect to height, which is the region where most of the weather phenomena takes place. So now suppose, so we are now considering a more realistic case where we are considering the decrease in temperature with respect to height rather than considering an isothermal atmosphere. Now suppose there is an atmosphere where temperature decreases linearly with height. Now we are considering the temperature is decreasing linearly with height at the rate of 6.5 Kelvin per kilometer. This will be negative because the temperature is decreasing linearly. Since it is a decrease, it will be minus 6.5 Kelvin per kilometer. What will be same height? What will be the pressure at a height of 4 kilometer? So again, the height is same 4 kilometer. We will take the same conditions that the surface pressure is 1000 hectopascal and the surface temperature as 288 Kelvin. Okay, now here the difference is that instead of considering an isothermal atmosphere, we are considering the temperature is decreasing with respect to height, which is basically known as the lapse rate. It is represented by gamma. It is given as minus 6.5 Kelvin per kilometer. Now the equation, this also we derived in the last class. The first one was in case of an isothermal atmosphere and this is in case of an atmosphere where the temperature is having a lapse rate gamma. Is given by P is equal to P0 into T0 minus gamma Z by T0 the whole raised to G by gamma into R. So here we know what is P0, which is 1000 into 10 raised to 2. T0 is 288 Kelvin minus gamma is having a value of minus 6.5. This Kelvin per kilometer into Z. Since it is a different that doesn't, okay, kilometer we have to convert it into meter. So it will be into 10 raised to minus 3 into 4000, which is the value of Z, divided by 288, the whole raised to G by gamma R, which is becoming a bit. G is having a value of 9.8 divided by gamma is again 6.5 into 10 raised to minus 3 into R, which is 287. This is a bit, can you try to solve this? Actually, you can solve in step by step. Can you guys try to solve? I am not going to solve the question. You guys can take your time, solve it, and then see. So, and just see what is the difference between the values that we are getting. So, in the first case, we were considering an isothermal atmosphere, which was an ideal case, which is not a realistic case. And we got at 4 kilometer, the pressure will be around that's 22 hectopascal, right? Now, in this case, this is a more realistic case where we are considering that the temperature is decreasing with respect to height. And in this case, such 22 you got, same value we are
Mm.
getting.
No, ma'am. It was the first value, 622.
Okay,
Was-
okay, fine. Okay, yeah. So just see how much it is coming and like how much difference is there with this and the first one. When we are considering a realistic one and when we are considering that more of a assumption, isothermal assumption. Okay, so solve the problem and let me know. Now we will solve another question. Yeah. So given that the mean atmospheric pressure, the mean atmospheric pressure at Earth's surface is 985 hectopascal. A. Find the total mass of Earth's atmosphere. B. Find the mass above the 500 hectopascal pressure level. Okay. So, given that the mean atmospheric pressure at Earth's surface is 985 hectopascal, how will we denote surface pressure? Like in the last two questions, how did we denote the surface pressure? What was the variable used or what was the notation used?
P naught.
P naught. So P naught is given as 985 hectopascal. So we want to find the mass of Earth's atmosphere. So in the first case, we want to find the mass of the total atmosphere. So suppose this is Earth and and this is the surface which is P0, which is at a pressure of 985 hectopascal. Now we have the atmosphere. So we want to find the mass exerted by this atmosphere at the surface. The force that is exerted by the whole atmosphere over the surface. So what is pressure? Pressure is basically force per unit area, right? Per unit area, what is the force exerted by a body? That is given by pressure. So in this case, the force is basically mg or the weight of the air column above the surface. So the pressure exerted by the atmosphere on the surface is basically the weight of the atmosphere on the surface. So it can be written as mg by A. So now we want to find m, right? M is the weight of the whole atmosphere that is exerting a force F on the surface. So we have to solve for m, or m bar we will just put m bar is equal to pressure into area by G. So pressure is given as 985 hectopascal, right? So it will be 985 into 10 raised to 2. And area, so this is for one area, like a single per unit area it has given. The total area will be 4 pi into RE square. RE is the radius of the earth, which is 6,400 into 10 raised to 3. 6,400 kilometer it is. So to convert it into meter, into 10 raised to 3. 4 pi r square divided by g, which is 9.8. So now can you calculate and tell me what will be the weight or mass of the atmosphere? Did you get anyone? So basically pressure is a force exerted per unit area. So in this case, we already earlier also we have learned that pressure is basically the weight of the air column just above that particular layer. It is a force exerted by or the weight of the air column above that surface. So it is given by mg by A, and we have to find m. So m is given by pressure into area by G. So surface pressure is 985 into 10 raised to 2, and area will be the total area of the earth, the total surface area that is in contact with the atmosphere, or the total area of the earth, which is given by 4 pi r square. R is the radius of the earth, which is having a value of 6,400 kilometer, or 6,400 into 10 raised to 3 meter, divided by G. What will be the value? Final value? How much kilogram it will be? Anyone?
92.877 into 10 to the power 10 kilograms.
Think something. I'm getting a value of 5.17 into 10 raised to 18. I hope this is correct. If anyone is getting a different answer, please let me know. I think people got a different answer. I think this is so if any okay. Soumya, which
Miscalculated.
okay, yeah. Soumya, which value you got? How much you got? You can just type also. I hope this value is correct, which is 5.17 into 10 raised to 18 kilogram. Just check if you are getting a different value, please let me know. Okay, so this was the first question A. Now the second one is find the mass above the 500 hectopascal pressure level. So initially we found the mass of the whole atmosphere, and because we put P as 985 hectopascal. Now there is another layer which is at a height of 500 hectopascal. So in this case, the force will be the weight of the atmospheric column above this layer. Only above this layer need to be considered. Below it doesn't exert a force. So just the air weight of the atmosphere above the 500 hectopascal layer will affect the pressure at that level. So in that case, our equation, same equation, mass will be 500 into 10 raised to 2 into 4 pi and the 6,400 into 10 raised to 3, the whole square divided by 9.8. So the difference is, instead of 985 hectopascal, in this case the level at which we are calculating is 500. Pressure level is 500 hectopascal. So it will be 500 into 10 raised to 2 into 4 into 3.14 into 6,400 into 10 raised to 3 whole square divided by 9.8. How much it will be? So we just replace 985 by, okay, 5.713, yeah, into 10 raised to 18, right? There is a power. I think Sami also got 5.17 for the previous one. So just put the power also. I think it is 10 raised to 18. So 5.17 into 10 raised to 18 is the answer for the first case. And now this case, what will be the answer? In this case, when we are calculating the weight of the or the mass of the atmospheric column above 500 hectopascal air, how much the value will be? It will be basically around 2.62 into 10 raised to 18 kilogram. 2.62 into 10 raised. So the mass has reduced as we go up as expected. So the value will be 2.62 into 10 raised to 18 kilogram. I hope you guys got the answers and the concepts are clear. So initially we calculated the pressure. Okay. Okay, 2.62 into 10 raised to 8. Okay. I hope the concepts are clear. Initially, we considered, in the first question, we considered an isothermal atmosphere. And then we calculated, okay, what will be the pressure of the surface temperature is 288 Kelvin and the surface pressure is this much. So we considered that temperature is constant over the whole layer. And in the second case, we considered the temperature is actually decreasing with respect to the height at a rate gamma. And then we try to calculate the pressure. So we haven't found the answer. Do the calculation and let me know what is the answer. And then third one, we just found the mass of the atmospheric column above the Earth. Okay. So now let's just discuss some more concepts. So we learned about the incoming solar radiation, with the help of Wien's displacement law, which is lambda max into T, we found uh, into T is equal to a constant. We found what is the maximum wavelength at which the solar radiation is being emitted. So we got the value around 500 nanometer, I guess, which is basically in the visible region. So when we look at the solar spectrum, we can see that the sun, solar radiation, the yellow line basically shows the wavelengths at which the sun the energy corresponding to each wavelength in the solar radiation or energy spectrum. So we can see that the sun is emitting radiation in all wavelengths, but the energy is peaking in the visible range. As we can see, the yellow line is peaking, the energy is peaking in the visible range, which is basically 400 to 700 nanometer, which we numerically also we calculated based on Wien's displacement. So even though the sun solar radiation covers the entire electromagnetic spectrum, the highest the wavelength at which the energy emitted is maximum is in the visible range of the spectrum. And if we have a more wider look, we can see that the highest is visible, and also UV and infrared are also being emitted by the solar radiation, which are the two other important components of the solar radiation. When we are talking about atmospheric science, or when we deal with meteorological processes, the three important wavelengths that we generally consider is the first one is the visible, where the solar radiation peaks. The second one is the ultraviolet range of the spectrum, which is basically absorbed by ozone in the atmosphere. Third one is the infrared range. which is basically the reason for heating or warming that is happening. So this is how the energy spectrum or the solar radiation spectrum is basically distributed. So when we look at the solar energy, almost 30, 43%, 43% of the incoming solar radiation falls in the visible range of the spectrum. 7% falls in the ultraviolet region, and 37% falls in the infrared region. So this is how the solar radiation is emitted. So now we discussed like earlier, the visible part of the radiation coming from the sun does not interact with any of the gas molecule in the atmosphere. It comes directly to the surface. So the visible radiation without interacting does not interact with atmosphere. I'm sorry, I think I lost the connection again. The internet connection is so bad today. Till what you heard, you guys remember? Till what? I don't know when I lost the connection.
Until ultraviolet radiation.
Okay. Uh, so I was telling like even though the solar radiation, the sun emits radiation in all ranges of the electromagnetic spectrum. Three most dominant ranges in which the solar radiation is being emitted is the visible, ultraviolet, and the infrared range. In case of visible, 43% of the incoming solar radiation falls in the visible range of the spectrum. 7% of the incoming solar radiation falls in the ultraviolet region of the spectrum, and 37% falls in the IR range, and all other radiations falls in the remaining part. Okay, so and when we discuss mostly about atmospheric processes or meteorological parameters, these are the three most important wavelength ranges that we generally consider. So the visible radiation does not interact with the atmosphere, with any gas molecule in the atmosphere, and it passes through the atmosphere without being affected. Or we can say the atmosphere is completely transparent. The atmospheric gases or the gas molecules present in the atmosphere is completely transparent to the visible rays, to the visible region. The gas molecule doesn't interact with the visible region of the spectrum. Okay, so basically the gas molecules have particular wavelengths to which they interact, like they absorb the radiation. So that is basically known as the selective absorption. So different gases will interact with the radiation differently. So it is highly specific to the certain spectral bands. Like this selective absorption of the gas molecules are highly specific to certain spectral band or wavelength ranges. So generally the atmospheric gas molecules, which is mostly composed of the nitrogen, oxygen and other greenhouse gases, are generally transparent to the visible radiation, which means as the visible radiation passes through the atmosphere, the gas molecules does not interact with it and it passes without being affected through the atmosphere. Whereas, and it directly comes to the surface, the radiation which is emitted in the visible range. Whereas terrestrial radiation, peak terrestrial radiation or the infrared radiation also comes through the atmosphere without being affected by the uh, atmosphere. Whereas the UV region of the spectrum, as we know, will be absorbed by which gas, particularly which gas interacts with the ultraviolet region of the
Ozone
spectrum?
layer.
Ozone layer. So ozone layer get absorbed in the stratospheric region and it doesn't reach the surface. It reduces this UV rays which are basically reaching the surface. So as so visible will be the atmospheric gases are mostly transparent to the visible region of the spectrum and also the far infrared region, some part of the infrared region also, and the UV region is basically absorbed by the ozone. So all other rays except the ozone, except the visible region, all the other the rays ray the radiation which falls in the other region of the spectrum reaches the surface without interacting with the atmosphere. Now, once these solar radiation, reach the surface, the Earth absorbs the radiation and will re-emit. So, as the Earth absorbs the radiation, the temperature of the there will be a temperature to Earth, and based on that, it will emit the radiation. So, lambda max into T is equal to constant. In case of Earth, the temperature is, let's assume, as 15 degrees Celsius, which will be around 15 plus 273, will be around 288 Kelvin. So Earth, which is having a temperature of around 288 Kelvin, will start re-emitting the radiation with the maximum radiation at a wavelength of around 10 micrometers. So the radiation that is being emitted back by the Earth, or the outgoing radiation from outgoing terrestrial radiation, will have a peak around 10 micrometers. So this outgoing terrestrial radiation is basically known as long wave because this falls in the long wave region of the spectrum. So when we look, so in this figure, this basically shows it in terms of increasing wavelength, and this is the energy intensity. So this region shows where the energy peaks in case of incoming solar radiation. And as we can see, this is happening in the visible, even though ultraviolet and infrared regions are also there, but the highest energy is associated with the visible range of the solar radiation. Whereas in case of Earth, so this blue region shows the wavelength or the terrestrial radiation which is being emitted by the Earth. So in this case, we can see the energy is peaking at a wavelength of 10 micrometers. So this falls in the long wave region of the spectrum. So basically the outgoing terrestrial radiation is known as outgoing long wave radiation, whereas the incoming solar radiation is known as incoming short wave radiation. Since this mostly falls in the short wave region of the spectrum, or short wavelength region of the spectrum, whereas the outgoing terrestrial radiation falls in the long wave region of the spectrum. So incoming short wave and outgoing long wave. So incoming shortwave radiation peaks in the visible range with the wavelength of 500 to around 500 nanometer, whereas in case of the outgoing long wave radiation, it peaks in the infrared region, which is 10 micrometer, far infrared region basically. So that is how the wavelength distribution or energy distribution of the incoming solar and outgoing long wave radiation. Now there is another interesting concept which is known as atmospheric wind. So as I said, the gas molecules have selective absorption, which means they absorb only certain specific wavelengths, or they only absorb radiation which falls to specific wavelengths. So atmospheric window is comes from this particular property of the atmospheric gas, or particularly of the gases. As I said, not all wavelengths of the electromagnetic spectrum from the sun reach the earth, and not all wavelengths emitted by the earth reach into space. So as the incoming solar radiation is coming, the atmosphere absorbs some of this energy while allowing another energy to pass through. So in case of the incoming solar radiation, it allows the visible and infrared region to pass through, whereas it absorbs the ultraviolet region of the spectrum. Whereas when we are talking about the outgoing long wave radiation from the earth, most of the atmospheric gases, or the greenhouse gases, are what do you say, selectively absorb the outgoing long wave radiation. So the greenhouse gases basically absorb the outgoing long wave radiation, which result in the warming that we are seeing, like global warming and all those things. So greenhouse warming is good if uh, we need the greenhouse gases to keep the earth at a reasonable temperature. If there was no greenhouse gases, the earth will be very cold. So we need the greenhouse gases. Greenhouse gases are very much important for the survival of life on earth. But the issue is, like, when the amount of greenhouse gases in the atmosphere is increasing, that is leading to more warming. So minimum or some amount of warming is required, but the increase in the amount of greenhouse gas in the atmosphere is leading to an enhanced warming, which is basically known as a global warming. So the places where the energy passes through are called atmospheric windows. The region of the electromagnetic spectrum where the atmosphere is transparent is basically known as the atmospheric window. And these regions are used to peer into the atmosphere. So if we want to know something, some characteristics of the earth, or we want to measure something in the earth from satellites, the satellites generally use radiations which falls in these atmospheric windows, because those will not be absorbed by the atmosphere. So it will directly pass through the atmosphere and reaches the surface. So atmospheric windows are very much important in case of satellite measurement and all. So atmospheric window is basically the region where the atmosphere is transparent, or where the atmosphere allows the incoming radiation to pass through. So visible region is one of the atmospheric window that we have, which is almost transparent to the radiation. So the dips in the incoming and outgoing energy that we see here are where the atmosphere absorbs energy. Some of the incoming energy is absorbed by the atmosphere, whereas most of the IR energy emitted by the earth is absorbed. Yeah. So mostly the visible region is the atmospheric window, where the atmosphere is almost transparent to the radiation, whereas it absorbs most of the radiation which falls in the IR region, or the outgoing long wave radiation. The atmosphere is totally opaque to the outgoing long wave radiation, and is totally transparent to the incoming short wave radiation. Now let's see another important uh, parameter, which is known as the albedo. So albedo is basically the percentage of radiation that is being reflected by the earth or some surface. So suppose there is 100 percentage of incoming solar radiation. Among this, let's say 30 percentage is being reflected. The solar energy is coming, we have the earth. Some of the incoming radiation will be reflected back. So let's say 30 percentage is reflected back, and 25 percentage is absorbed by the surface. So among the 100 percentage, suppose 25 percentage is being absorbed, and 45 percentage reaches back to space. So suppose this is how the incoming solar radiation is being divided. So this 30% which is basically being reflected back is known as the albedo. So the amount of radiation that is being reflected back to the space is known as albedo. Amount of radiation so this is either expressed in terms of percentage or in terms of fraction, which has a minimum value of 0 and maximum value of 1. So if we say a surface has an albedo of 1, it means all the incoming radiation that is incident on that particular surface is being reflected back. So generally when uh, we say the earth is having an albedo of 0.3, which is an average of all the surfaces we have on earth. So earth, if we consider the earth, it has different types of land use land covers. So each land use has different type of albedo. Suppose if we consider water, in case of water, which is basically a dark surface or it appears black from the outer space. In a satellite image, generally water appears to be black, which means water absorbs most of the radiation which is incident on it. Then we have forest covers or vegetation green covers, which is having a albedo in between 0 to 20%. So if you can see in this here, this basically gives in terms of the percentage and for different land use land covers. So the water is having the lowest albedo or reflectivity, which is close to 0, whereas forest is having 10%, which means 90% is being absorbed by the forest, whereas 10% is being reflected back. And then we have sand. Sand is having an albedo of around 30%, which means 30% is being reflected back and 70% is being absorbed. And then we have snow surfaces which are mostly white. So the things that appear mostly white will generally be having high reflectivity. So old, like if it is old snow or ice, it is having a lower albedo. Clouds which appear to be white is having an albedo of 80%, which is almost 80% of the radiation is being reflected back. And fresh snow is having an albedo value close to 1, which means most of the radiation incident on it will be reflected back. So the albedo is related to temperature as well. So if we say a surface is having a higher albedo, it means it will be at a lower temperature, just like snow, because it is not absorbing any of the radiation that is incident on it. Whereas a lower albedo indicates higher temperature, which means it is absorbing most of the radiation incident on it, which will eventually lead to an increase in the temperature of the object. So that's how the albedo is distributed in that. So these are the values of albedo for different surfaces on Earth. So water is having the lowest and snow is having the highest. Okay. So that is about albedo. Now, I think the concepts are clear. We discussed what is selective absorption, which means each of the atmospheric gas or all gases have a particular wavelength or region of the spectrum in which they to which they interact. Most of the radiation which falls outside this absorption layer will like the gases will act transparent to those radiation. Then we talked about atmospheric window. Atmospheric window is that region of the spectrum to which the atmosphere is almost transparent to. So some radiation of that particular wavelength is coming towards the atmosphere does not interact with it and it almost pass through without any change. So that windows or that range of wavelength are basically known as the atmospheric windows. For satellite measurements, we generally utilize the atmospheric window to study about the Earth. So, and that is atmospheric window. And then we learned about the term albedo. So, albedo tells you how much amount of radiation incident on a surface is being reflected back, with Earth having an average albedo of around 0.3 or 30%. It is basically an average of all different surfaces that we have on Earth. I think all these concepts are clear. Now let's move on to a different topic, which is basically forces, different forces which are relevant in meteorology or that we generally use when we are talking about atmospheric science. So first we will look at the different classifications of forces, which is basically first let us classify it into surface force and body force. So surface force uh, acts on the boundary between two surfaces. It is independent of the mass of the object. And then we have body force, which acts on the center of mass of an object. And then it is basically like directly proportional to the mass of the object. So suppose there is a body M which is on a surface like this. Force that is acting on the center of mass of this object is known as body force, and the frictional force that is acting on the boundary between the object and the surface is Fs as a surface force. So the examples of surface force include friction, viscosity, etc. And the example of body forces include gravitational force. Okay, so these are two different classification of force. Then there is another way of classifying it, which is real force and apparent force. So this is basically based on the frame of reference of the frame of reference which we are considering. So in case of real force, it basically occurs in an inertial frame of reference. Inertial frame of reference in the sense frame of reference which is moving, which is at rest or is moving with a uniform velocity. And Newton's laws are valid in the inertial frame of reference. And apparent force generally occur with respect to a non-inertial frame of reference. Non-inertial frame of reference in the sense which is moving in uniform, which is moving at a uniform acceleration, which is basically an accelerated frame of reference. That is non-inertial frame of reference. So real force generally occurs in inertial frame of reference, which is the frame of reference which is at rest or of uniform motion. And apparent forces come into play when we are considering non-inertial frame of reference. which is basically moving at uniform acceleration. So Newton's laws are valid in inertial frame and it is not valid in non-inertial frame. So whatever forces are coming in the inertial frame of reference are called real forces. Example are pressure gradient force, pressure gradient force, gravitational force, frictional. And the example of apparent force which basically act in non-inertial frame of reference include Coriolis force, Coriolis, and the centrifugal. Yeah, so those are the different classifications of forces. Now let's see different types of forces that are involved. So the first one is a pressure gradient force. Deepak, you have a doubt, Deepak?
Yes, ma'am.
Yeah, please ask.
Ma'am, real force is the force that has a constant acceleration, and apparent force is the force that doesn't have a constant acceleration. Is it, ma'am?
Yeah, uniform acceleration.
Okay, ma'am. Thank you, ma'am.
Accelerated, yeah. It does, in case of real force, it is not accelerated. It will be mostly moving with a uniform velocity. Uh, but in acceleration will be zero. Uniform velocity at there won't be acceleration associated with an inertial frame of reference. Whereas in case of non-inertial frame, it will be an accelerated frame of reference.
But, ma'am,
Acceleration
in the
will be
example
zero.
of
Acceleration will be zero in case of inertial.
But ma'am, in the example of real force, we have written gravitational force, and it has an acceleration of 9.8.
Okay, it has okay. Oh, oh yes, uniform velocity in the sense either the acceleration is uniform or it is zero, right?
Yes, ma'am.
Okay, yeah, then constant acceleration or okay. I'll check it. I doubt if it includes accelerated. Uh, like the frame of reference won't be. Okay, let me check if it is uniform acceleration or acceleration is oh, the thing is like the object can be accelerated or there will be an acceleration associated with the force. the frame of reference will not be accelerating. Like the frame of reference from which we are observing will be at rest or of uniform velocity. The frame of reference won't be accelerating, but accelerated motion can happen um, like within that frame. The thing is that the frame of reference which we are considering won't be accelerated, but the object could have an accelerated motion. Suppose we are like mm, suppose I'm standing and then I'm moving up. Then I'm observing that a bus is moving or a bus is moving from a bus stand. So my frame of reference is with respect to my frame of reference. So my frame of reference basically an inertial frame of reference because I am at rest. I don't know if I'm
Okay,
making any
so
sense.
ma'am, yes, ma'am, I'm getting it. I think, ma'am, the frame of reference will not change irrespective of the force in real force. But in apparent force, the frame of reference also changes. Like if we
Yeah.
move from southern hemisphere of the Earth to northern hemisphere, then the direction of Coriolis force will change itself. So with the
Um,
place, it doesn't change, I guess. In
mhm.
real force.
So yeah. So in case of a inertial frame of reference, the frame of reference will be either be at rest or of uniform velocity. Yeah, suppose as I said, I'm at a bus stop and I'm seeing that a bus is moving or something. So the bus can have an accelerated motion. So I'm looking from a frame of reference which is at because I am at rest, so it is at rest. Suppose I'm observing the same thing from outer space or something. Then in addition to the acceleration of the bus, there will be we have to consider the rotation of the Earth or the Earth's um, acceleration also. So since Earth is having a angular velocity, that also we have to consider. So if I'm observing from space, then the Earth's rotation also need to be considered. Then it becomes non-inertial frame of reference. But if both of the objects, so if I'm observing within the Earth, I'm observing another object which is being accelerated. Both me and the object are moving along with the Earth. So then it becomes an inertial frame of reference. When I'm observing from outer space, the um, rotation of the Earth also need to be considered. So then it becomes a non-inertial frame of reference. So in that case, we are considering a frame of reference which is moving along with the Earth, which is basically accelerating. So that is a non-inertial frame of reference.
Okay, ma'am.
I don't know if I made you more confused or you understood.
Yes, ma'am, understood.
So, okay, that is about real forces and apparent forces. Now let's look at the different forces that we are considering. The first one, as I told, so we will be discussing four different forces. Pressure gradient force, viscous force, third one, is the Coriolis force, one, the gravitational. So I won't go into the derivations, which is already discussed in the NPTEL class. I will just give a glimpse of what each of these forces are, which you have already learned in your class. So the first one is the pressure gradient force. I think we have discussed about this in the last class. Suppose we have Earth, and at the surface we have a surface pressure around suppose 1000 hectopascal, and there is another layer which is at 985 hectopascal. So there is a force which is, there is a gradient in the pressure which is from, is having a direction in this direction. So because of this gradient, there will be a force that will be acting, which is basically known as a pressure gradient force, which is having a direction opposite to that of the gradient. So this arises due to difference in pressure. So this force basically arises due to the difference in pressure, and the equation of the pressure gradient force is given by minus 1 by rho del P, where rho is the density. So dou is coming because we are considering the force in unit mass, force per unit mass we are considering. That's why the 1 by rho term is coming. So del P basically gives you the variation in pressure. So del in the sense in all three directions. Dou P by dou H psi plus dou P by dou I G plus dou P by dou Z K. In all three directions, what is the gradient in pressure? That's what del P gives. And then 1 by rho is basically coming because we are considering the force per unit mass. So this is the pressure gradient force which is given by minus 1 by rho del P. And we discussed the hydrostatic equation in the last class, I guess, which is basically this equation is very much important in atmospheric science. Actually, this is dP by dz is equal to minus rho g. This is basically the pressure gradient in the vertical direction. So the del P, we are considering only the vertical direction. The change is only in the vertical direction. Then it is dP by dz is equal to minus rho g. Generally, when we consider in the atmosphere, the pressure gradients in the vertical direction is very much prominent rather than in the x or y direction. So when we move from surface to a particular height h in the atmosphere, the pressure changes will be very high. But when we move from um, suppose like in that along the latitude or along the longitude, the changes will be comparatively less compared to that of the vertical gradients. So this basically shows you how the vertical pressure gradient is being balanced by the gravitational force, which is G. So this is the hydrostatic equation, which is basically a balance between the vertical pressure gradient force and the gravitational force G. Dou P by dou C or dP by dZ is equal to minus rho G. So pressure gradient force is given by minus 1 by rho del P. That is the first force. Now, second one is a viscous force. Which, yeah. Suppose consider there is a column in which a liquid or fluid something is filled, and this layer which is at the bottom is fixed. This is having a velocity 0, whereas this moves with a velocity u. The upper plate moves with a velocity u, whereas the lower plate is fixed and which is at rest. And there is a liquid, incompressible liquid, which is filled between these two plates. So the particles close to the above surface, the particles which are close to this surface which is having a velocity u will try to move along with the surface, whereas this particles will basically try to remain at rest, which is close to the plate which is at rest. It will try to remain at rest. So the force that needs to be applied on the upper plate to move it with velocity u0, the force uh, that needs to be or that is being applied at the upper plate to move it at a velocity u is given by, and this distance between the two plates is given by L length. So that force which is required to move the upper plate is directly proportional to the area of the plate directly proportional to the velocity and is inversely proportional to the length of the fluid column, which is L. Now F is directly proportional to A U by L. So there is a when this proportion sign changes to equal to, there is a constant which comes, which is F is equal to mu A U by L. This constant mu is known as dynamic viscosity coefficient. Okay, this is the viscous force. The unit of mu is given by Pascal second or Newton second per meter. So that is the viscous force. Now the third force is the gravitational force. So gravitational force comes into play due to the force of attraction between two bodies which are capital mass capital M and mass small m. Suppose they are located at a distance of small r. The force acting on the two bodies is given by Gmm by r square, and the direction of the force will be in this direction, r direction. R Gmm by r square. So as we are basically considering the forces per unit mass. So it will be F by m, which will be Gm by r. What is Gm by r square? Gm by r square will be G, or the acceleration due to gravity that we are considering. So the gravitational force is nothing but when the gravitational force that is acting per unit mass is nothing but the acceleration due to gravity itself. So this is generally having a value of 9.8 meter per second square, right? Now when we are considering atmospheric motions or movements, generally the air parcels move along the vertical direction. So this is surface which is at a distance of r from the center, and then suppose the air parcel which is at the surface is moving to a height h, and the acceleration due to gravity at the height r and the height h will be different. So what will be so g star, let it be the gravity acceleration due to gravity at a height h. So it will become g star is equal to gm by r plus h the whole square, which is basically gm by r square into 1 plus h by r the whole square. This will reduce to gm by r square into 1 minus 2h by r, or g star, which is basically the acceleration due to gravity at the height h, is the acceleration due to gravity at the surface into 1 minus 2h by r. So and for an air parcel which is at a height h from the surface, this will be the value of acceleration due to gravity. Now let's consider or let's calculate what will be the acceleration due to gravity h. What will be the acceleration due to gravity g star at a height of 10 kilometers. So when we discussed about the vertical structure of the atmosphere, I told you like most of the atmospheric processes occur in the troposphere itself, which is basically within a height of 10 to 12, 10 to 14 kilometers. So suppose we are considering an air parcel which is such a height h, which is equal to 10 kilometers. What will be the acceleration due to gravity at that height? Let's see. So g star is g into 1 minus 2h by r. G, what is the value of g? Acceleration due to gravity at the surface?
9.8.
9.8 into 1 minus what will be h?
10.
10 into 10 raised to 3 by r. What is r?
6400.
6400. Again it is in kilometer. Yeah. So now can you calculate and tell me how much it will change within that height of the troposphere? How much the acceleration due to gravity change?
Nine point seven three meter per second square.
So there is a change of around 0.03 meter per second square, which is very negligible. So generally when we consider atmospheric motions, we consider the value of g as 9.8 itself, since the change is very less. So most of the atmospheric motions that we are considering or the weather patterns that we consider fall within the first 10 to 11 kilometer only. Since the variation in g is very much negligible within that height, we generally consider g to be 9.8 itself. Okay, so generally when we talk about atmospheric motion, the g that we consider is 9.8 meter per second square. So we use this assumption for like for EC calculations and it is very much negligible even if we consider the difference. So that is the gravitational force. Now the fourth one is the Coriolis force. So Coriolis force is an apparent force because it is explained in terms of a non-inertial frames of reference or an accelerated frame of reference, which is basically our Earth. So the Earth itself is rotating, and this force is associated with that frame of reference. That's why this is called a Coriolis force. It comes from the rotation of the Earth. So Coriolis force is coming acts due to the rotation of the Earth, and it acts on an object moving with velocity v. Only on an object which is moving with velocity v will have this Coriolis force. If a body is at rest, the Coriolis force won't act on it. So let's see what is the Coriolis force. Suppose this is Earth. This is the equator, which is 0 degree. Okay, before discussing the Coriolis force, we will just discuss some of the conventions that we use when we are considering motions in the atmosphere. Some of the atmospheric variable conventions. So this is the Earth. This is north. This is south. This is east. This is west. So are the four directions that we have. And then we have another direction which is upward in the atmosphere and downward in the atmosphere. So we have three different dimensions. Okay. So this north-south dimension or the movement in the north-south direction is generally represented by y, or it is basically considered as a y direction. And the movement in the east-west direction is considered as, so this is y or j cap. This east-west is generally x direction or I cap, and the z direction is basically upward and downward motion in the atmosphere, which is z. This x cap or I cap, x direction. This is the j direction, and upward and downward movement in the atmosphere. Vertical movement in the atmosphere is the z direction or k cap. Okay, so these are the three different directions in the atmosphere. And when we look at the sign convention, which is positive, which is negative, and all those things. So suppose a body is moving from south to north. Suppose a body is moving from south to north. This is considered to be the positive x direction. Sorry, positive y direction. Now, suppose a body is moving from north to south. If we are moving from north to south, it is considered as a negative y direction. Now, when we talk about east-west x directional movements, so when a body is moving from west to east is positive x direction, and east to west is negative x direction. And in the z direction, upward motion, if we are moving, the parcel is moving from the surface to a particular height h. Upward motion is positive and downward motion is negative. And another important convention is the north-south movement is basically known as meridian, is basically told as meridional direction, and east-west direction is known as zonal direction. So the north-south is meridional and east-west is zonal. And Z is basically the upward direction, upward and downward direction. So these are just some of the sign conventions that will be helpful when we go forward. Okay, so we were talking about the code. And one more thing, suppose a body telling that a body is having a velocity v on earth. It is component, three different components, vi plus vj plus vk. So vi will tell you how it is moving in the north-south direction. Vj will tell you how it is moving in the east-west direction. Vj will tell you how it is moving in the north-south direction. Vk will tell you is it moving upward in the atmosphere or it is staying in the surface. So yeah, Coriolis force. So initially I told you this is an apparent force. This is due to the rotation of the earth. And it acts on an object only when the object is moving with a velocity v. It doesn't act on an object which is at rest. So this is Suppose an object is present at a latitude 5. This is the latitude 5. An object is present on the surface of the earth at a latitude of 5. Okay. And the angular velocity at this point. And we know that the earth is rotating with an angular velocity omega, right? This is the direction of the angular velocity. So the earth is always rotating with an angular velocity omega. Now we are considering an object which is situated at a latitude of 5 from the equator. So the angular velocity that is acting upon this object will be, so this is the direction of the angular velocity omega. So if we are considering this object, this is the x component. Here we have the y component. So if this is 5, this will also be 5. I'll just draw it once again. Just so messy. Yeah, I think I'm very bad at this. So this is our equator. This is the axis of rotation. Earth is rotating at an angular velocity omega. We have an object here at a latitude of 5 from the equator. The angular velocity will be acting in this direction, perpendicular to the surface. So this is the x component. This will also be 5. This will be the so the angular velocity, the acting on the body at a latitude 5 can be given as, so it basically will have two components. It can be given as omega cos phi j plus sin phi k. So it will basically have two components, one along the y direction, which is omega cos phi j, and one along the k direction. So this is k pointing away from the surface of the earth. So that is k. It is given by so it will basically have two components, omega cos phi j and omega sin phi k, or omega into cos phi j plus sin phi. So this will be the angular velocity that is acting on an object which is at a latitude omega from the equator. So what is the magnitude of omega? What will be the value of omega? Omega is basically the angular velocity of the earth, which is given by 2 pi by t, which is 2 into 3.14 by 24 into 3600, which will be, what will be the angular velocity of earth? Can you calculate and tell me what will be the angular velocity of the earth?
Ma'am, what is that? 2 2 into 3 1 3.1.
It is angular velocity is given by 2 pi by t, right? 2 pi is the how much time it will take to complete one rotation. That is the angular velocity. So 2 pi is the total distance that it covers by t, the time it takes.
Okay, ma'am.
So 2 pi by t will be distance by time basically. 2 pi by time period of time period of oscillation. What it will be? Can you tell me the value?
7.268
Yeah,
into 10 to the power minus 5.
yeah. So it will be 7.29 into 10 raised to minus 5 second inverse. So this is the value of omega, which is the angular velocity of the Earth. So angular velocity of any planet can be calculated this way if you know the value of t. So if you know how much time it will take to complete one rotation, then you can calculate the value of angular velocity by simply using the equation 2 pi by t. So in case of another planet, t will change. What will be the time period of rotation for that particular planet? You just have to substitute, and then you can find the angular velocity of that particular planet. Just I don't know. I think the figure is still wrong. This is the angular velocity omega. This is the equator, 0 degree north. This is the phi. We have an object over here. This is the k direction. This is the phi, and this will be omega. This will be the y direction. This is omega. We have to along k and y. We have to find what are the components. So if this is phi, this will be 90 minus phi, and this will be phi. So this is the so this along the y direction it will be cos phi j, and along the k direction it will be sin phi. Sorry, along the y direction it will be sin phi j, cos phi j and sin phi k. Along the y direction it will be cos phi j, and along the k direction it will be sin phi. This is the adjacent and this is the opposite side. I think the figure is clear now. Earlier it was wrong. So this is yeah, this will be phi, this will be the k direction, this will be y, this will be the direction of omega. It will be just parallel to this line. Omega will be parallel to this north-south direction. I think the figure is clear now. So omega will have two components, which will be omega cos phi j plus sin phi k along the k direction. And the value of omega is 7.29 into 10 raised to minus 5 second inverse. So this is the angular velocity. Now what is Coriolis force? Coriolis force Coriolis force is basically given by minus 2 omega cross b. So what does it do? Coriolis force acting on an object deflects the object to the right, to its right in the northern hemisphere and to its left in the southern hemisphere. So basically, suppose an object with the velocity v is moving from equator to the pole. This is how it should go. This is how it's supposed to go in a straight line, but due to the Coriolis force or due to the rotation of the Earth, it will take a slightly deviated path like this. It will deflect towards its right and it will reach over here. So in the northern hemisphere, the deflection will be towards the right of the original path, and whereas in the southern hemisphere it will be towards the left. This is happening because of the rotation of the Earth. So this will come into play only when the object is moving. Only when the object is having a velocity v, Coriolis force will come into play. As we can see from the equation, it has a component v. Suppose v is equal to 0, then F Coriolis will not be acting on the object. So only if the object is in motion, we will have the Coriolis force. Now, so this doesn't come into play when we are considering the motions that are happening in short scales. Like suppose I'm throwing a stone from, like I'm throwing a stone, then it doesn't, when we are playing cricket and all, then during that time we are not able to see this deflection because the scale of motion is very small. But when we are considering the motions that we are happening at very like large scale, like a aeroplane is moving from, suppose it is moving from Kochi to Bhubaneswar, or from like Delhi to Kochi or something. Then at that time, this forces comes into play because that is large. It is happening at a large scale of motion. It is not a short scale. So when we are considering short, and the scale of motion or the distance that it travels is very small, it is very short scale motion, then these things doesn't come into play. But when we are considering long, um, the motions that are happening at a larger scale, then these things come into play. Then only these things will come into play. Okay, so yeah, that is Coriolis force. So you can calculate. So this is basically the cross product. V is Vi plus Vj plus Vk, and omega, is basically component wise, if we separate, it is omega cos phi j at a latitude phi, omega cos phi j plus omega sin phi k. Now, if you do the cross product, you will get the component wise equation for the Coriolis force. Yes. It is cross product Ijk 0 omega cos phi omega sin phi u v and w minus 2. Yeah. So can you calculate the cross product and tell me what it will be? Minus 2 omega into, along the I direction, it will be omega w cos phi minus this into this v sin phi along the I direction, minus j, along the j direction it will be 0 minus u omega sin phi. It will be u sin phi in the j direction minus, along the k direction it will be u omega cos phi, u cos phi into k. minus 2 omega is outside. So in terms component wise or along different directions, F Coriolis can be written as minus 2 omega into omega cos phi minus V sin phi, which is along the I direction, plus U sin phi along the J direction minus U cos phi K along the Z direction. So this is the Coriolis force in terms, this is common, minus 2 omega is common. So this is Coriolis force in different, along different direction, different component price. Okay, I think I will stop here today. I had a couple of problems related to the Coriolis force. I think we will solve it in the next class. If you have any doubt, you can ask me, or we will wind up for today.
I will read on that, ma'am. And if I'll have some doubt, then I will ask in the next class.
Oh, yeah, sure. Thank you. Thank you. Bye.
Thank you, ma'am.